Topic video 7, C Programming for Embedded Systems. The goal of this topic is not to teach you C, but to sort of fill in the gaps so that if you're already a competent C programmer, how can you take that knowledge and apply it to an embedded system? So to be able to understand how to do that, we need to know how a C compiler actually works so we can see what the missing bits and pieces are of the puzzle that we need to fill in order to be able to write successful C code for an embedded system. So what actually happens when you compile your C code? Effectively, what happens is you have a series of utilities that work together to basically translate your code from its source origins, whether it's a C source code or assembly source code, and simply translate them through a series of steps into our binary source code that can be directly interpreted and executed by our processor. Okay, so there's a series of steps that we actually go through in order to translate our C code or assembly code into this binary executable. There is a preprocessor, which does some initial sort of steps, and then that generates an intermediate source file that is then passed on to either the compiler or the assembler, depending on what you originally wrote the code in. The compiler then does a further translation from one form to another. It's then creates an object file, and then using a link within, we can then tag all those object files together and simply make a binary executable file. So I'll talk about each of these stages in a bit more detail. So what is the role of the preprocessor? Well, effectively the preprocessor performs a series of tasks. First of all, it expands any macros that you may have defined in your C code. So if you've got any hash defines, it simply does string replacement through your C code. So it basically generates an intermediate C program in which all the hash defines are expanded. It also inserts all the includes into your file, so all your hash includes are actually inserted into the C file as well. And effectively all these stages that it does, the hash defines, the hash includes, basically it generates an intermediate C file that is then passed on to the actual compiler. So when the compiler gets this intermediate C file, it effectively needs to translate the C code into assembler and performs optimization on that assembly code. So when it gets your standard C control structures, it simply replaces them with a library of assembly code. So it has a template of assembly code for each one of the major control structures. So when you use a control structure, it simply does a substitution with that assembly code and simply generates an intermediate assembly file. And then once it's generated that intermediate assembly file, it can then do a bit of optimization on it. So maybe it goes through and sees, oh, hang on, I haven't used these registers, or I don't really need this code, it's sort of obsolete, and it can sort of reduce the amount of instructions and sort of try and in some way make the code a bit smaller or make it a bit faster. And of course, once you've generated that assembly code can't be directly interpreted by the processor, so we need to go through that final stage of actually converting that assembly code into the binary executable code that our processor will actually understand. So it actually generates a relocatable binary, so it generates a chunk of assembly or machine code that can effectively be placed anywhere inside our memory. So it currently doesn't have any hard-coded memory addresses. So it's a chunk of binary code that can be stored anywhere in our target, because we haven't actually defined where we're going to stick all these bits of binary yet. So we haven't allocated any spaces, we haven't allocated where it's going to be on the target, so we've sort of haven't quite finished the task at hand yet. We also have access to an archive utility, so we can tell our compiler to actually build this particular piece of code that we're writing, but don't worry about linking it, don't worry about making an executable binary out of it, just make a binary code out of it, but just store it away for later use. So we can actually get it to make a library, so we can get it to archive it up so that later on when we write a program, we might want to use these libraries, so therefore we've already got this library pre-compiled, ready to go. So instead of having to rewrite your code all the time, you try to write your code in such a way that you can have a series of libraries that you can just utilize each time. The more libraries you have for each different subsystem or each different action, I guess, the quicker you can prototype your code, the quicker you can get a solution up and running. So archive utility provides a facility to be able to compress the binary and stick the binary away in some sort of library that we can use later on. Okay, the final stage of our compiler is effectively the linker and locator stage. So this is by far the most important stage of the whole process, because up until now all we've done is just simply generate a chunk of little binary components that have no idea of where they're going to be stored. They have no size limitations. We haven't actually done any checking to see whether, of course, all these little chunks that we've actually built so far are even going to fit on our target. So the whole role of the linker and locator is effectively to work out where the code and our variables are going to be stored on our target processor. So our linker needs to have a very good idea about our memory map of our target. So when it comes to our code or our program, this is generally allocated into ROM, okay, and our variables that we've used in our code are generally allocated into RAM. So the linker needs to have a very good picture of where our ROM is and how big it is, where our RAM is and how big it is, so therefore it knows where to stick these various components and to check whether in fact we have enough resources to fit these various program and variable components. So the linker also checks to ensure that the code is small enough to fit inside the ROM of the target. So simply it joins all those binary components together. So if we've got multiple files and we've generated binary components for each of those files, and then we've got to the linker and we want to join all those files together, it will join all the files together, and then it will check to see the size of how much memory all those files are going to require on the target, and then also check to see that the target has enough space. If it doesn't have enough space, it will give you an error, and therefore you've got to go back and either optimize your code either by manually going to your code and removing instructions, or simply by optimizing it when you compile it by giving it a few compiler optimization switches to reduce your code size. The linker also ensures that there is enough space and RAM for both our program variables and also our stack space. So it'll simply go up and add up the total number of variables that we're using, and it will also go and add up our total amount of stack space that we're using, add the two together, and make sure they're actually going to fit inside our RAM space that we have at our disposal. Because when you pass parameters on a function in C, so all those arguments in a function header, when you pass them, when you do a call to a function, those arguments are passed via the stack. And any local variables we have inside a function are also put onto the stack as well. So during compile time, our compiler can go through, it can see what the biggest function is as far as arguments are concerned, and it can calculate the total amount of stack space we're going to require for that. It can also check to see how many local variables and see how much stack space we're going to need for that. So basically it can calculate what the total amount of stack space we're going to require in our program, and it can also do a quick check to see if we can fit both our stack space and our variable space inside our RAM location on our target. If we can't fit it, then of course it'll give us an error, and the compiler can't really help us out in that situation. We'll actually have to go back to the code and actually look at our code and think, hang on, I don't really need a short for that variable because it's only going to go up between 0 and 200. Hey, I can use an unsigned char to hold that value instead. So it's a matter of going back and having a close look at your variables and picking appropriate sizes for each of the variables to try and get every last little bit of saving out of your RAM space. So now that we've got a basic idea of how the compiler is working, we need to know how to create a successful build system. So the most important thing that we require is a host system. Okay, we can't run the compiler and the editors and so forth on our actual microcontroller that we're trying to program. So we actually need a host computer that can host our build software for us. So the host system should have a cross compiler. Okay, and a cross compiler effectively is a compiler that runs natively on the host, but builds binary for our target. So commonly used cross compiler is the M68 HC12 GCC cross compiler, which runs under Linux on an Intel host, but it makes binary code for our microprocessor. Also require a set of target libraries. These are optional, but if you've got target libraries, then you don't have to go and reinvent the wheel when you're communicating with all the various subsystems. If you've got libraries, then you can just simply use the pre-built libraries and you can generate code very quickly. It's an optional thing because some people like to make their own libraries. I personally like to make my own libraries so I can actually know exactly what's happening. I can optimize them down to get every last little bit of space out of my memory. Also require a debugger of some kind, so whether this is a JTAG or a BDM debugger, but some sort of mechanism that we can use to interact with our target to help us debug our code, or maybe even a simulator or an emulator that we can run on the host that will emulate our target, and we can actually see how our code's working. So not only do we need to be able to build the binary code for our target, but we also want to be able to debug that code to see exactly what's happening. And of course, the last thing is, once we've built that binary code, we're going to need to get that binary code in one form or another onto our target. So we'll need a loader of some kind. So a binary loader to simply go type in or click a button to say, put this binary code that I've just written or compiled, assembled, and stick it on my actual platform, my target. So a binary loader simply will do the communication between the host and the target and facilitate the whole loading of that binary into the target, so therefore then you can simply run your code on that target. Okay, so therefore, what does the system actually require? So now that we've had a bit of a think about the compiler and we can sort of see how that's sort of working, there's a few things we need to actually provide that compiler so it can successfully create software for us. So what does the build system effectively require? So basically, our compiler is going to need to know some information about our target. It will need to know things like, where is the memory for code located? So where can we stick our program instructions? Where should our variables go? So where can we stick those variables? How much space do we have for our program and how much space do we have for our variables? So we need to have a very clear idea of our memory structure of our target. So therefore the compiler can generate appropriate binaries that can fit in those various components. So it can generate our program into the right region and make sure it fits, generate our variables into the right region and make sure they fit. And we also need to know how can we access the I/O registers from inside our C program. So normally when you're writing C program, you're using a series of pre-built libraries like printf, file open and things like that. When it comes to embedded stuff, we don't have those libraries. How do we interact with the various I/O subsystems on our platform? So we'll look at how we can do that. How can I set up the interrupt vector table? Because that's extremely important. You need to be able to know where the reset vector is set. So therefore, when you turn the processor on, it actually runs the right piece of code. So how can I set up that interrupt vector table to tell the compiler so that it makes my code properly so that it actually runs? How can I also embed assembly instructions into my C code? So if I actually, written it in C, but they're saying, I guess I want to have some really finite sort of delays. I really want to have some real precise delays in my code. How can I insert a few nops here and there? Okay, so how can I just insert some assembly into my C code? So these are all the questions we need to ask, and these are the questions that we're going to answer over the next few slides. Okay, so when it comes to telling the compiler everything we know about our memory layout of our target, we utilize a mechanism called a memory map. Well, effectively, it is a memory map. A memory map refers to how our memory is actually laid out on our target. So therefore, we have a means of describing this memory map to the compiler. Well, effectively, we need to describe it to the linker. It's the linker part of the compiler that needs to know where everything has to go. So many mainstream integrated development environments actually allow you to define the memory map through a series of project settings in a menu. So you can just simply fire up a dialog box, put in your RAM start, how long it is, and so forth. So you can actually define it inside the dialog. So depending on what sort of IDE you're using, the way that you actually define it can be completely different. When you use Code Warrior, the actual memory map is done automatically. So when you actually fire up the wizard and you actually choose what processor it is you're using, that automatically generates the memory map for you. So therefore the assembler and the C compiler actually knows exactly where each component of your code needs to go and knows the size limitations. When it comes to using a GCC compiler like the M68 HC12 GCC compiler, we actually have to define our memory map using a text file. And this text file simply consists of a description, so to speak, of our various components of our memory. So we use the keyword memory, we have a curly brace which we use to define the various components of our memory. So we define, inside this file, we define a page 0 chunk, and the page 0 refers to our I/O registers, and we tell origin keyword says where that component starts, and we have a length to define how long that component is. So our page 0, our I/O register starts at the bottom of memory at 00, and it is 2K in length. We then have an E squared prom section, which we don't generally use. We have an E squared prom section. We define that to start at C00, and it's a length of 1K. So we can define an EEPROM. We then have the text keyword, and it's that text keyword that tells the compiler that, hey, this is where you should stick the program data. So when you compile your C code and it needs to put your program instructions somewhere, it'll put them in the text section of where you've defined in the memory map. So we have text, and we define it to be read, write, executable. So that's what the bit in the brackets means. We define the origin to be at 4000 hex, okay, and we say the length is 16K. Okay, so therefore when you use a C compiler, it's going to put your code, your program instructions at 4000 up until 16K in length. And then of course we need to tell it where it can stick our data, our variables. So we have a keyword data to define our RAM or variable space, and then we say where that chunk of memory begins at 2000 hex, and we say how long it is, it's 4K in length. So these components actually clearly describe the various components of our memory map to the compiler. The last line there, which is provide stack, basically tells the compiler where we should stick our stack. So when you compile your C code is going to require use of the stacks. Every time you jump to a subroutine, it needs to push variables on the stack. If an interrupt takes place during the running of the program, then of course it's going to need to push context on the stack. So you need to define what the stack is going to be, and we generally do that inside memory.x. So we say provide stack at 3FFF hexadecimal. So that's the last memory location of RAM, because our stack starts at the end and it works back towards 0. So we simply define the last memory location in our RAM to be the start of our stack. So when you compile your C code and it needs to set up the stack inside the C code, which is usually done as part of the initialization portion of C, it'll simply point the stack to the last memory location in our RAM. So that's the way we can describe our physical memory layout of our device to our compiler. So therefore the linker's got everything that it needs to know in order to be able to create a successful program for our target. When it comes to accessing our I/O registers inside C, okay, there's difficult ways and there's easy ways of doing it. One way is you can simply generate pointers to point to the various memory locations and then simply dereference those pointers, which is similar to what we do in this example that I'm showing you, but I'm doing it in such a way that you can very easily abstract the complexities of using pointers. So we need to be able to define inside C, we can define variables that reside in predetermined memory locations. So we can simply set up pointers to memory locations and then dereference those pointers to a particular variable name. So So as I've said it in the notes here, I've actually said we can assign a pointer to a particular location. So if we know, say, port A is at the memory location 000, we can assign a pointer to that memory location, and then we can dereference that pointer and assign that whole thing to a particular label name. And therefore we can just utilize that label name to simply interact with that particular location. So since most of our I/O registers are 16-bit in size, because most of our I/O registers are actually 8-bit in size, we can actually typecast them to unsigned chars, because unsigned chars are also 8 bits in size. If we're trying to refer to a memory location that is 16 bits in size, and we do have a few of them, then you'd probably want to sort of typecast them to an unsigned short pointer, which is 16 bits in size. But generally, most of our I/O space, or our I/O memory locations, are all 8 bits in size, or registers are all 8 bits in size, so we simply typecast them to unsigned chars. And also, because our I/O registers are not constant, they change as a result of external events. So if you're talking about a GPIO I/O register, so like the data register for a GPIO port, and if it's an input-only port, then those values can change whenever the values on the pins actually change. So because these registers effectively change beyond our control, we simply define them to be volatile, okay, which in our case doesn't really make much difference whether you make them volatile or not. But if you're using a processor in which it uses a caching mechanism, then it basically tells the compiler not to believe anything that it's cached. So if you've got a memory location sitting inside cache, it basically tells the compiler that you've got to simply reload that cache each time you try to access that variable, because it could have very easily changed. So volatile basically forces the processor to simply reread that I/O register every time that you want to read from it. So it simply neglects whatever it might have in cache. But in our case, we don't have cache, so it makes no real difference whether we put the volatile keyword in there or not. But generally, it's good practice to put it there, because you may be using a system down the track that has cache, and therefore you want to force the processor to actually reread it from the memory instead of reading it out of a cache somewhere. Okay, so therefore we can map an I/O register to a variable in the following fashion. So we've simply mapped a memory location to a label name. So we have a hash define. We simply define the label name. Okay, so in this case we're trying to make a variable, so to speak, called port A, in which it actually resides in the memory location of port A, which is at 000. So to sort of reverse engineer this line, if you start on the rightmost end, we have the memory location, which is 0000 in hexadecimal. We have then typecast that memory location to be a pointer of unsigned char. So that's what that bit in brackets defines it as being unsigned char. Okay, so therefore that memory location we've basically said that memory location is a pointer of type unsigned char, which it is. It's an 8-bit location, so it's a pointer of unsigned char. And then in front of those brackets, we've got a little star again. So therefore, we've dereferenced that pointer, which means that we effectively want to make port A the contents of that unsigned char memory location called 0000. So effectively, we've gone and made that 000 a unsigned char pointer. Okay, so we've mapped it to an unsigned char pointer, and therefore then we've gone and dereferenced that pointer by putting a star in front of it. So therefore, we've simply assigned a label called port A to be that contents of that memory location at 0000. So therefore, when it comes to accessing that port A register, we can then simply access it as if it was a normal C variable. Okay, so therefore we can read from port A by going C equals port A, so we can deal with it like it was a normal variable. We can write to port A by going port A equals some value. So depending on whether we put that label on the left-hand or the right-hand side of the equal sign, we're either writing to it or reading from it. So if it's on the, just to reiterate that, if it's on the right-hand side, we are reading from it. If it's on the left-hand side of the equal sign, then we are writing to it. And that's effectively how we can make any of our IO registers simply a variable, so to speak. We can simply generate a series of hash-defined lines and typecast them to unsigned char pointers and then dereference them. So we can simply put the appropriate memory location on the very end of that hash-defined line, and then we can put the appropriate label name just after the hash defined. So therefore you can simply map all of your IO registers to appropriate named labels, so to speak. Okay, so one of the other things we want to actually do in our C code is we want to actually be able to set up our interrupt table as well. So we need to be able to facilitate interrupts inside our C code. So not only do we want to be able to read and write to our IO registers, we need to be able to, get the thing to work in the first place. So we need to be able to set up the reset vector. Otherwise, if we don't set up the reset vector, we can upload our code, push all the buttons on the target to try and get it to run, but it's just not going to work. Okay, so we actually need to not only get the code going into the right locations, and we need to have access to our various IO subsystems, but we also need to be able to set up the interrupt vector table to ensure that the program starts appropriately. So when we're actually doing interrupts inside C, we can simply, when we define our interrupt service routines, we simply define them as standard void functions, so they're void ISR void, okay? But if we define it in such a way as void ISR void, it basically assumes that it's a standard C function. So our compiler will actually go through and go, void ISR void, yeah, it's just a standard C function. Therefore, on the end of that function, when I translate it to assembler, I'll just stick an RTS, and therefore it'll do a return from subroutine. So effectively, we need to tell the compiler that, hey, yeah, this is like a subroutine, but it's actually an interrupt service routine. So therefore, you need to deal with it differently. So in order to tell the compiler that, hey, when you get to the end, instead of sticking an RTS on this end of this subroutine, put an RTI, we've actually got to tell the compiler that it actually is a nice interrupt service routine. So there's numerous ways in which we can do that. So depending on which compiler you're actually using, the way you might have to define that a particular subroutine is an interrupt service routine can in fact differ. So it pays to look it up in the actual manual for that compiler. But I've given some examples here of when it comes to using GCC, or also using the tasking 8051 compiler as well. So when it comes to using the GCC compiler, we can define a subroutine as being an interrupt service subroutine simply by using the void attribute interrupt keyword in front of the subroutine's name. So we have double underscores before the attribute, we have double scores after the attribute, and we have no spaces between the double brackets. So it's simply underscore underscore attribute underscore underscore bracket bracket interrupt close bracket. Then it's simply the name of our subroutine. Call it whatever you want, and then it's simply the void in the brackets so that we don't have any arguments. Because, like I said before, we pass no arguments into an interrupt service routine, and we can get no arguments back from an interrupt service routine because we can't use the stack, we can't use the we can't use the registers because, during an interrupt, the registers are preserved, they're restored at the end of the interrupt service routine, and our stack must remain exactly as it was before. So we can't pass any variables forward or back from an ISR. But we can do it using global variables. That's something different, completely different. So some compilers link the ISR to the vector table automatically for you when it comes to using the tasking 51. One of the arguments you provide to the interrupt, the line when you define it as an interrupt, you can actually define which interrupt you actually want to set it to, and therefore the compiler will automatically set it up for you. But when it comes to doing it in GCC, we have to do it manually. Okay, we have to explicitly define the interrupt vector table for the compiler. So when it comes to doing it in GCC, we define the interrupt vector table using GCC's assembly. So we use the assembly that GCC provides to define our interrupt vector table. So when it comes to defining our interrupt vector table, we define it using GCC assembly. So inside this GCC assembly file, we call it vectors.s. Okay, so therefore it defines it as a vectors file, and the .s defines it to be an assembly file. So .s is generally what GCC uses to define assembly. So what we have in there is have our .global vectors. So this is a label that defines to the C compiler that this is our global vector table. We've then gone global vectors address, so therefore we've actually defined what the location of this vector table is going to be. We've set up the vector address to point to FFFF0, okay, and then we've defined a variable called def, which we're going to set up to be 0, and so therefore def is the value we're going to use at any location in our vector table where we haven't actually set up, or we're not actually using that particular portion of that vector table. So to begin with, we're actually starting with the dot word def. The dot word is equivalent to our dc.w in our HS12 assembly. So effectively you can think of these as all dc.w's, and therefore we've got effectively dot word def, which is equivalent of dc.w0000. So therefore we're actually zeroing out the elements of that table that we're not actually using. And what's after the semicolon is in fact a comment. But because we've set the vector table to start at FFF0, these comments in fact sort of define what the actual memory locations are of this vector table that we're actually modifying here. So what we've actually done is we've actually zeroed out FFF0 because we're not using it. The second element, we've got dot word ISR. ISR is the same name as our interrupt service routine that we defined before a few slides earlier. Okay, so therefore we can actually make the connection between that routine and a particular location in our vector table simply by putting that label of that routine in the vector table. And then we've defined all the other ones to be 0 except for the last one, which has got a dot word underscore start. Okay, and that is because the last element in there, the FFFE, is in fact our reset vector. So we have to set up the reset vector. Otherwise, when you upload this code onto your target and you try to reset the target, it's not going to run. So therefore, we always put dot word underscore start, because underscore start is the chunk of C code that runs just prior to your main routine. So the underscore start routine actually sets up things like our stack, sets up our, things like our clock or any other sort of things that absolutely definitely have to happen before you run your C code, and then it simply calls your main from inside that underscore start routine. Okay, so therefore underscore start is always put in there. If you simply put your main name in there instead of underscore start, then of course your code will start up without a stack and some other crucial things. So it's always good to leave underscore start there. Okay, so now that we've defined our memory map, we've defined how to interact with the I/O registers, we've also defined how to set up our vector table. So the last thing we really want to be able to do inside our C program is insert our assembly into C somehow. So if you want to include assembly code into your C program, it can be done using a keyword called ASM. Each compiler is different, so it pays to look it up. Here I've given an example of the Tasking 8051 compiler and how you can actually interact with these, like include assembler into the compiler using this sort of structure. So we can use a keyword ASM, so we can underscore ASM, then you can specify as a string what particular instruction it is that you want to run. Then you can define what output operand, so if that instruction generates some data that you want to get back, you can then specify what the output operands are, so what variables you want to pump that data back into in your C code, what input operands, so which variables, so if you're using instructions that require input from the C code, then you can specify what the variables are that provide the input, and then of course you can provide also a list of clobbered registers, so you can also provide a list of registers that are used inside your chunk of assembly code, and that way the compiler can make sure that it preserves those contents, or ensure that if it's going to use registers around your assembly code, that it sort of uses other registers, or if it's forced to use the same registers, it preserves them by pushing them on the stack and restores them after your bit of assembly code. So it sort of lets the compiler know what your register usage effectively is. So when it comes to doing it in the GCC compiler, it's effectively the same thing, except we don't have the double underscore in front of the ASM keyword. It's simply ASM, open the brackets, the particular instruction we want to use, and then the output operands, the input operands, and then the list of clobbered registers as well. So that's how we can do it. So the output, input, and list of clobbered registers are all optional arguments to ASM. So if you just want to simply have one particular instruction that you want to run, so let's say you want to run a NOP inside your C code, then you can simply put the NOP inside inverted double quotations. So to give you an example of using assembler inside GCC, this is an example pulled straight out of a third year computer systems subject. And effectively inside here, what we're trying to do is, as a result of an interrupt taking place, we have our entire CPU context stored on the stack. This chunk of code here actually grabs that context off the stack and simply puts it into an array called tasks. So effectively, each line of this is simply grabbing a particular value out of the stack and storing it into a particular memory location. So you can see here, I've got a load D, 8, stack pointer, so this effectively loads the condition code register out of our stack into accumulator D. So the ASM command here, LDD 8, SP, loads that condition code register, 16-bit condition code register, into accumulator D. And then I've got a \n/t, which means we're on a new line, and we've tabbed across, which means we're actually back in the opcode column. And then I simply go store D %0. So that simply wants to store the contents of D at some memory location where the %0 defines the number of, the argument list for my particular output operands. So if you go to after the double quotations, you've got two colons. So the first colon separates the input arguments, which I don't have. So there is nothing in the first chunk there. So I've simply gone colon. So therefore now I'm talking about output operands. And therefore I have a M in brackets, which defines this is a memory location as opposed to another register. So I said this is a memory location, and the memory location is, in brackets, whatever this sort of variable array record combination thing, whatever memory location that effectively points to. So that is where I want to store the value of D in that particular memory location. So you can see that we do this for every single bit of our register. So we store the condition code register, we store the accumulator D, we store index register X and Y, we store the program counter, and of course we also store the stack pointer as well into this particular array record inside this array. So this is a way that you can embed assembly code inside your C code. So the first argument of ASM is you define the actual instruction. So you can define multiple lines of assembly code simply by putting a \n/t after one line, and therefore it can have multiple lines. We can define our input operands. So in this example here, I haven't used any input operands, and I've made that very clear by putting two colons side by side. You can define the output operands. So you define the M to define its memory location. Then in brackets, you put what that particular location is you want to store it to. And therefore, I haven't actually told the compiler which registers I've clobbered, because I've just made sure that this is inside an interrupt service routine anyway, so I don't really have to care about which registers are clobbered because they're preserved and restored around this code automatically anyway. So, pros of using C code. So when it comes to using C inside our, to talk to our embedded target, the pros, of course, are it allows fast software development, so you can write code up very quickly. So you're just writing a very simple hello world or something can take place very quickly inside C. It's easy, readable code. C code's a lot easier to read than assembly code. Of course, it's not like reading a novel, but of course it's a lot more readable than assembly code. Unless, of course, you're an absolute fanatic commenter like me and you simply turned your assembly code into basically a story anyway. But effectively, C is a lot easier to read than assembler. Also, by using a C compiler to develop code for an embedded platform, we have access to C profilers and debuggers. So we can actually run our C code through a profiler. Profiler can say, hey, this subroutine that you've written here is taking up 80% of the CPU time. So therefore you can look at it and think, okay, well, all right, I better rewrite that so I don't spend all my time inside that routine. So you've got access to profilers when you write it in C, and you've also got access to some pretty good debuggers inside C as well. You can always prototype it on the host as well, so you can write your C code on a host, so you can have a series of I guess, interface routines that sort of are emulated by the host, so you can see how the code runs on the host, and then of course once you're pretty sure it's running perfectly on the host, then you can translate it into C code for your actual target. Of course, it's simpler to write C. Some people think it's simpler to write assembler, but generally from a starting point it's simpler to write C, and of course you have better error detection as well. So when you're assembling or compiling your code, the code can come back and say, hey, you've exceeded your memory locations for your program, or you've exceeded your memory locations for your data. Whereas when you do an assembler, you can simply have all this data inside your assembly code and it can simply exceed the amount of RAM you have. There's no error checking for you. So C provides a facility to do a little bit more error checking, and also gives you a little bit more feedback if you've done something wrong as well. Okay, the cons of using a C compiler, of course, we have limited control over the resulting binary. Yes, you can use a whole heap of optimization switches and sort of guide the compiler in a certain way, but you have no absolute control over the binary code that's actually generated. Whereas when you come to using assembler, you can explicitly define every instruction in assembler, and you can explicitly define how the code is generated just simply by using the opcodes that you want to use. Simplest programs inside C suffer from bloat, so even if you're just doing the simplest like hello world sort of example in C, you've got all these additional libraries and the code just bloats out something bad. Every time you're jumping into a subroutine, you're generating a frame stack for that subroutine, and you've got all this extra code that's being thrown in there just to facilitate that frame stack. So writing the most simplest codes in C can result in an extremely huge binary footprint. So you need to make sure that if you're only doing very simple code, it's probably best to do it in assembler, otherwise you end up with a big chunky bloated binary. But then again, if you're using a target that's just got heaps and heaps and heaps and heaps of memory resources, what does it really matter? The code tends to run slower if it's been written in C for that very reason. You've got all these extra chunks of code that's been generated to facilitate stacks, facilitate other components of the C program, so therefore the code will generally run a bit slower. If you run it in assembler, it'll run a lot quicker. So generally when you're writing a chunk of code for an embedded platform, you probably would write the majority of it in C, but then you'd look at the most critical components of your code, or if you've run it through a profile and you found out one routine is monopolizing your CPU and basically spending most of its time in there, then you might take that routine, or you might take your critical bit of code and say, hey, I'm going to rewrite this in assembler because I need it to happen very quickly. So there is always a need, even though C is probably the better way to go when writing code for embedded platforms, there will always be a need to embed assembly code inside your software somewhere, and it will generally be the most critical chunk of code that will be written in assembler, or the chunk of code that you actually need to optimize to make run a bit faster, you actually put it in assembler. So code is generally bigger in size when you write using a C compiler, and of course compilers can be expensive, unless of course using the GCC compiler, which is at the best price known to man, which is free. But generally compilers, commercial compilers can be very expensive. Also, it can be difficult when mixing assembler with C. So when you've got assembly code in there and you've got C code, you've really got to have a very clear idea about how the C compiler is working to know exactly how you can move data around. So generally when you're using assembler embedded with C, you'll generally get the compiler to spit out the assembly code, and then you'll have a look at the assembly code to make sure that your assembly code that you've written fuses correctly with the assembly code that the compiler generated. So generally it can be very more difficult incorporating both C and assembler together in the same file. So when it comes to putting all these components together to get a successful program running, I've gone through an example here of using the GCC compiler to basically go through step by step how you could actually put all these bits together to make a program. Okay, so the first thing is to ensure that you've got the appropriate compiler. So there is a GCC 68HC1X compiler. Okay, so if you install that and you install the bin utils that also come along with that compiler, then you basically got the basics compiling system that you require. You can get these from the GNU website. Okay, they're in RPM format, so you can simply grab them off the website, install them under Linux, and you can make use of them. So first things you need to do is you need to create the memory.x file to clearly describe the memory of your target, and I've already given you the example of that memory.x file already in this lecture topic. We also talk about do the vectors.s file, so you can also generate that. So if you're using the IRQ interrupt mechanism, then you leave that line in the vectors.s. If you're not using it, then simply null it out. But generally, we've given you the vectors.s file that will give you the basic access to the reset vector. So first of all, the thing you need to do is then assemble the vectors.s file. So you simply get that vectors.s file, you run it through the M6811 GCC assembler, and you tell it what target to build that assembly binary code for. So in this case, I've told it to build it for the HCS12, which is what we're using. I've said that our architecture is based around a 16-bit architecture, so I've said -m short, and then I've given it the assembler file vectors.s, and then I've told it the output file to make vectors.o. So after running that command, I will have an object file called vectors.o, which I can then incorporate later on when I'm doing my C compiling. So then what I do is I then type in a very simple C program where I simply set up port A to output some data. So I simply define the port A data register to simply be the memory location 0. I define the data directional register variable to be the memory location 2, which is the location of the actual data directional register for port A. I then write a little main code which simply has a variable called A. We simply set up the data directional register to be purely output, and then I simply do on a while one, I simply increment the variable A and store that value onto port A. So simply the value on port A will start at 0, go all the way up to 255. When it hits 255, because 255 is the maximum value you can have an 8-bit register, it will automatically roll over back to 0. So I'll have it going 0, 255, 0, 255, 0, 255, 0, 255, and just keep repeating that sequence of events. So I've called this file test.c. So then what I need to do next is I basically need to compile that code. So therefore I need to ensure that I have the memory.x and the vectors.s file in the same directory as what I'm currently compiling. So therefore I simply hit the compiler by typing in the M6811 ELF GCC line. I define the architecture type to be my processors. That's what the two -m options are. I include my vectors.o and my memory.x file, and I simply hit that line, and it simply will make an ELF executable of my binary program that I've written. So it'll make an ELF binary executable of my C code. It's not really all that useful for uploading to a target right now because it's in an ELF format. So what I can do is I can simply use the object copy, and using object copy I can effectively tell it to translate that ELF file into an S19 file. And an S19 file is a text file that can be directly interpreted and read by our target. So therefore I can then upload that test.s19 file. So that resulting S19 file, as I said, we want to upload that to our target. We can upload that to the adapt 9S12X using a Linux tool called binload, okay? And you can get a modified version of this binload program from the demonstrator if you really want to go through and try this for yourself. So should you require any further assistance, please do not hesitate to ask your demonstrator. Post a question on the forum, email me, the convener, make an appointment to see me, but no matter which way you choose to go, please make sure your questions get answered.